Okay, day 2. So today we're going to look at more direction angles, which we looked at toward the end of last night's video. We're going to look at vector forces and some applications. So the big thing we want to be able to do by the end is take a vector and split it up into what we call its component forces. We're also going to look at another notation for vectors, which is what we call trig form. So that's the first thing we're going to look at today is trig form. So first, direction angles. So if u is a unit vector such that theta is the angle measured counterclockwise from the positive x-axis to u, then the terminal point of u lies on the unit circle. So that should hopefully make sense if we think about what is a unit vector. A unit vector is a vector with a magnitude of length 1, and the unit circle is a circle with a radius of 1. And when we talk about angles on the unit circle, we always start with 0 on the positive side of the x-axis, so then our theta is the same theta that we've been dealing with angles on the unit circle. So some notations for u is in component form. We could write it as xy. We could also write it as the cosine of theta times the sine of theta, because the cosine of theta will equal the x component, the sine of theta will equal the y component. And we could also write it as cosine of theta I plus sine of theta j, where again theta is what we refer to as the direction angle. If v is any vector, then v equals ai plus b times j can be the magnitude of v times the cosine of theta sine of theta, or magnitude of v times cosine of theta I plus magnitude of v times sine of theta j. So this is our trig form of a vector. Again, it's just a different way to write a vector. All of these are the same thing though, and then we know tangent of theta is the sine of theta over the cosine of theta, which is the magnitude of v times the sine of theta over the magnitude of v times the cosine of theta, which is b over a. And again, we looked at that yesterday as well, so that's not new. Okay, so some applications to vectors. One is displacement. We also have velocity, acceleration, and force. So vector addition. We looked at this geometrically. Well, what does it mean in an application? Well, when vectors point in the same direction, we add them just as we would add any two numbers. So, for instance, if we have a vector that represents the velocity of an airplane, well, it's going to be the actual speed of the plane plus the speed of the wind, and that'll give us the resultant velocity of the plane. In this case, so if we had 100 kilometers per hour plus 25 kilometers per hour, the plane is actually going 125 kilometers per hour. When they point in opposite directions, then we can just subtract the two vectors. So the plane's velocity minus the wind velocity would be a resultant velocity of 75 kilometers per hour. The one thing you would want to be careful in these types of problems is making sure that the units all match up. If they don't, then you need to convert them so that they do. Well, what if the vectors are not going in the same or directly opposite directions? Then what do we do? Well, then we have components of what we call a resultant vector. So if they're perpendicular to each other, so if the plane is flying in this direction at 100 kilometers an hour, and the wind is the wind is going west at 25 kilometers an hour, the plane is going south, then we have a resultant vector that is going to be 103.1 kilometers per hour, and we get that just by doing the Pythagorean theorem, where we know 100 squared plus 25 squared equals r squared, and so that leads to this r value. These are what we would call vector components of the resultant vector. So whenever we're talking about vector components, they're always going to be components that form a right triangle with the resultant. So in this case, I could say this is my v sub y, because it's going in the y direction. So that's this right here, that's my 100, and then this is my v sub x, because it is going in the x direction, and then I have the resultant vector. Then what about the angle theta? So if this is my angle theta here, Notice that it is not based off of the unit circle at this point, but we can still find that angle using our relationship that we talked about 3 slides ago, where we know tangent of theta is b over a. So in this case, I can call this my b and this my a, so I know tangent of theta is 25 over 100. So then if I use my calculator, do tangent inverse, theta is approximately 14.036 degrees. Now this problem didn't ask for any sort of application. Right now we're just kind of going through the basic calculations to make sure we understand them, which we should because this is not new. This is just trig review at this point. But we could answer this question in the terms of bearings. So you could say south 14.036 degrees west, something like that. Or you could answer it based off of the unit circle. So based off the unit circle, this would be 255.964 degrees because it would be 270 degrees minus 14.036 degrees. Okay, so this is how we can find the resultant if we have the components. What if we want to work the other way? So in this case, in the last case, we can take two vectors and replace them with a single vector that has the same effect. This is the vector addition that provides us with what we call the resultant vector. And we can also start with a single vector and think of it as a resultant of two perpendicular vectors called components. So we can work backwards if we know the resultant and find the components. We can do this again using trig, where in this case if I know this is a 60-degree angle and I have some velocity here that's 50 meters per second, I know that the cosine of 60 is going to be v sub x over v, and the sine of 60 is going to be v sub y over v, where this is v sub x and v sub y. And then you could do those calculations in your calculator, and then they round to approximately 43 meters per second and 25 meters per second. I'm not going through the calculations, and I'm going through this kind of quickly because these calculations are, again, it's nothing new. We've been doing this all year long. Okay, let's look at an example. So if you're walking a dog and the leash is making a 40-degree angle with the dog's back and you are holding it with a force of 60 newtons, find the component vectors. So I want you to pause the video and try to find the component vectors for this scenario. Unpause when you're ready to check your work. I'll give you a hint. It's nice to draw a picture. And on a test or quiz, I would want you to draw a picture. Pause the video. Unpause when you're ready to check your work. Okay, so I have my dog, and the leash is hooked to the dog. This is a great picture. The leash looks like it's just kind of stapled into the back of the dog's neck. Don't worry, no animals were harmed in the making of this problem. So I have a 60 Newton force here at a 40-degree angle, so V sub x is this, and V sub y is this. So then I can do 60 sine 40 is V sub y, so that's 38.567 newtons. 60 cosine 40 is V sub x, which is 45.963 newtons. Let's try a little more challenging problem. So, find the angle between the forces given the magnitude of their resultant. So I have some force 1 that's 3,000 pounds and some force 2 that's 1,000 pounds. And I know the resultant of the two forces is 3,750 pounds. I'm trying to find the angle between them. Okay, well what can I do? Well, since I don't have any defined location for these forces, pick one of them and make it along the x-axis. That's going to be the easiest thing to do. So I'm going to call this force U, and I'm going to say that that's 3,000 I. And so then the other force, which I'll call force V, is going to be 1000 cosine of theta I plus 1000 sine, of theta j. And now I know that the resultant of these two, so u plus v, or I should say the magnitude of u plus v, so u plus v is going to be 3000 plus 1000 cosine of theta I plus 1000 sine of theta j. And so then the magnitude of u plus v, which is what I know is 3750, is the square root of 3000 plus 1000 cosine theta quantity squared plus 1000 sine theta quantity squared, and this equals 3750. So I've done the majority of this problem here. I want you to pause the video at this point and find theta. Unpause when you're ready to check your work. Alright, so we should end up with theta is approximately 47.384 degrees. So how do we come up with that? Well, we already had the magnitude equation written, so then it just became a solving process. Square both sides. When you multiply this binomial out, you get 9 million plus 6 million cosine theta plus 1 million cosine squared theta. This becomes 1 million sine squared theta. You could factor out a 1 million from there, and you're left with cosine squared plus sine squared, which is 1, so that's why those go away. Then bring everything over to one side, isolate the cosine, do the inverse, and we get theta. So again, the trick here, or I don't know if trick is the correct word, but the way to make this problem easier was originally when we set one of the forces on the x-axis. And we can do that because we just know that the relationship between the two forces is this angle theta. And so if this force is on the x-axis, then this force is theta degrees away from that force, because we're starting at the x-axis is 0 degrees. So then that's why for v we can just write that in our normal trig form, where it's the magnitude of v times the cosine theta I plus the magnitude of v times the sine of theta j. Alright, now I want you to try it completely on your own. So you have forces with magnitudes of 125 newtons and 300 newtons, and they act on a hook. The angle between the two forces is 45 degrees. Find the direction and magnitude of the resultant of these forces. Pause the video, unpause when you're ready to check your work. Oh, sorry, you might have already paused, but this one should be the 300, and this one should be the 125. The size of them was supposed to give you that hint, but if you didn't pick up on that, that's what they should be. Okay, so we should end up with a resultant magnitude of 398.319 newtons at an angle of 12.821 degrees. How do we come up with that? Well, I called this vector vector u, which ends up being 300i. Vector v is 125 cosine 45i plus 125 sine 45j, which is 125 root 2 over 2i plus 125 root 2 over 2j. So u plus v is 300 plus 125 root 2 over 2i plus 125 root 2 over 2j. We find the magnitude, type that into our calculator, we get the result. To find the angle, we do the tangent of b over a, and we get our angle. Again, also when you're doing these, make sure your answer makes sense. The resultant magnitude should be larger than either of the individual components here, and then the angle should be closer to the 300 than the 125. Okay, we're running out of time on this. We have one more example I want to do, so this is the end of part 1. Go on to part 2, and we'll do the last example.